Section: Introduction. In this section, we discuss iterative denoising methods like diffusion and flow matching, which have achieved great success in generating various types of data, including images, videos, audio, and proteins. However, these methods are often slow and costly due to their need for multiple passes through the neural network during inference. We believe there is a way to maintain the advantages of diffusion training while allowing for one-step denoising. We focus on an end-to-end approach, where a single model is trained to perform one-step denoising in one training run. Previous methods have used a two-stage process, which adds complexity and often requires generating large synthetic datasets or using multiple networks. Consistency models are closer to our end-to-end goal but depend heavily on extensive bootstrapping and careful training schedules. These two-stage methods also face challenges in determining when to stop training and start distillation, while our end-to-end models can be trained continuously for ongoing improvement. We introduce shortcut models, a new class of generative models that can produce high-quality outputs in a single sampling step, regardless of the inference budget. Our main idea is to condition the neural network not just on the noise level but also on the desired step size, allowing it to effectively leap forward in the denoising process. Shortcut models perform self-distillation during training, eliminating the need for a separate distillation phase and avoiding complex schedules. Training shortcut models is efficient, requiring only about 16% more computational resources than a standard diffusion model. Our evaluations show that these models meet several important criteria. On popular benchmarks like Celeba HQ and ImageNet 256, a single shortcut model can manage various generation tasks, including many-step, few-step, and one-step generation, without sacrificing accuracy. In fact, the quality of many-step generation matches that of traditional diffusion models, and shortcut models often outperform two-stage methods in fewer steps. To summarize our contributions, we present shortcut models that generate high-quality samples in one forward pass by conditioning on step size. Unlike distillation or consistency models, they are trained in a single run without a schedule. We conduct a thorough comparison of shortcut models against previous diffusion and flow matching methods on Celeba HQ 256 and ImageNet 256, showing that they match or exceed the performance of distillation methods that require multiple training phases and significantly outperform earlier end-to-end methods across different inference budgets. Additionally, we apply shortcut models to robotic control, replacing diffusion policies with shortcut policies, and find that they maintain similar performance at a much lower inference cost. In the background, we note that diffusion and flow matching models tackle generative modeling by learning an ordinary differential equation, ODE, that transforms noise into data. We simplify our approach by using the optimal transport flow matching objective. We define a linear interpolation between a data point and a noise point, with the velocity indicating the direction from noise to data. Given the noise and data points, the velocity is determined, but with only the interpolated point, there are multiple possible pairs, making the velocity a random variable. Flow models learn to estimate the expected velocity based on the interpolated point. While a well-trained ODE can deterministically map noise to data in continuous time, this certainty diminishes with finite step sizes. Flow matching predicts the average direction from the interpolated point to the data, but using a large step size can lead to jumping to an average of multiple data points. At the start, the model receives pure noise, and the training pairs are randomly matched, causing the predicted velocity to point towards the mean of the dataset. Therefore, even with optimal flow matching, one-step generation can fail for multimodal data distributions. Section Summary. In this section, we introduce shortcut models, a new class of generative models that enable high-quality sample generation in a single forward pass by conditioning on the desired step size, eliminating the need for complex distillation processes. We demonstrate that these models not only match the performance of traditional diffusion methods but also significantly outperform previous end-to-end approaches across various inference budgets, including applications beyond image generation. Section: Shortcut models for few-step generation. In this section, we introduce shortcut models, a new type of denoising generative model that reduces the number of sampling steps needed compared to diffusion and flow matching models. Our main idea is to train a single model that can handle various sampling budgets by conditioning it on both the current time step and the desired step size. We observe that flow matching learns a path that connects noise to data, but taking large steps can lead to significant errors. By conditioning on the step size, our shortcut models can better navigate these paths and reach the correct next point. We define the shortcut as the direction from the current point to the next point we want to reach. Our goal is to train a shortcut model that learns this direction for all combinations of the current point, time step, and step size. Shortcut models extend flow matching models by allowing for larger jumps. When the step size approaches 0, the shortcut aligns with the flow. Instead of simulating the entire process with small steps, which is computationally expensive, we utilize a self-consistency property. One shortcut step can be seen as two smaller steps combined. This lets us train the model effectively for larger step sizes while still using flow matching for small steps. We can train the model on any distribution of step sizes, but we typically divide our training data into two groups, one for small steps and another for larger, randomly sampled steps. This leads us to a combined loss function that ensures the model learns to generate data consistently across different step sizes. Next, we outline our training framework. We make design choices that promote stability and simplicity. For small step sizes, we train the model using a loss function that matches it to real data. We find that uniformly sampling time steps works well. To maintain accuracy at larger step sizes, we use self-generated targets and limit the length of our bootstrap paths by combining two smaller shortcuts to create a larger one. We decide on a number of steps to represent the smallest time unit for approximating the process, which we set to 128. During training, we sample the current point, time, and a random step size, then use two sequential steps to create our training target. When the step size is at its smallest, we query the model at 0 step size. Our training objective combines empirical flow matching and self-consistency, which we optimize together. We find that the empirical term has higher variance, so we use more empirical targets than self-consistency targets in our training batches. This approach also helps with computational efficiency, as generating self-consistency targets is more resource-intensive. We also incorporate classifier-free guidance, which has been effective in improving generation quality, but we limit its use to small step sizes. Additionally, we apply exponential moving average weights to smooth out the output and reduce variance, especially at larger step sizes. Weight decay is important for stability, particularly early in training, as it prevents the model from getting stuck on noisy targets. We find that proper weight decay eliminates these issues, allowing us to avoid complex training schedules. Finally, we streamline the training process by only sampling relevant time steps, focusing on multiples of the step size during training. This targeted approach helps us train the self-consistency objective effectively. Section Summary. In this section, we introduce shortcut models, a new type of denoising generative model that efficiently handles varying sampling steps by conditioning on both the time step and desired step size, allowing for larger jumps in data generation. We detail our training framework, which combines empirical flow matching and self-consistency objectives to ensure stability and accuracy across different step sizes, ultimately reducing computational costs compared to traditional diffusion models. Section: Distillation of diffusion models. In this section, we discuss the distillation of diffusion models. Previous research has looked into converting pre-trained diffusion models into simpler one-step or few-step models. Techniques like knowledge distillation and rectified flows create synthetic datasets by simulating the denoising process, but this full simulation can be costly. To address this, several methods have been developed that use bootstrapping to initiate the simulation. We also note that alternatives to the standard distance measures have been suggested for distillation targets, including adversarial and distribution matching objectives. Our approach is similar to binary time distillation methods, which break down the distillation process into stages that gradually increase in step size, thus reducing the number of bootstrap paths needed. However, we concentrate on training a one-step generative model directly, without separate pre-training or distillation phases. This makes our method less computationally intensive than full simulation techniques and eliminates the need for multiple teacher-student interactions found in progressive distillation methods. Next, we explore consistency modeling, which involves one-step generative models that learn to convert partially noised data into complete data. While these models can serve as students in distillation, they can also be trained from scratch using consistency training. Our approach addresses the same problem but differs in that consistency training can introduce bias at each step due to ambiguity. Instead, we sample from the learned ode to avoid this issue. Shortcut models require fewer bootstraps compared to consistency models, which need more steps. Additionally, shortcut models are simpler to implement, as they do not require some of the complex techniques used in consistency models. We then present a series of experiments to assess the quality, scalability, and robustness of shortcut models. Our findings indicate that shortcut models can generate high-quality outputs in few or one-shot scenarios, competing well with existing two-stage methods and outperforming other end-to-end approaches. They also maintain the performance of base diffusion models in many step generation. As we increase the model size, we observe continued improvement in generation capabilities. Shortcut models learn a flexible latent noise space and show robustness in applications like robotic control. In comparing shortcut models to previous one-step generation methods, we train each method from scratch using the same architecture and codebase, specifically the DIT-B diffusion transformer. We utilize datasets like CELEBA-HQ256 for unconditional generation and ImageNet256 for class conditional generation, employing the Atom-W optimizer with a consistent learning rate and weight decay. We compare against two categories of prior diffusion methods: two-stage methods that pre-train and then distill separately, and end-to-end methods that train a one-step model in a single run. We also evaluate various methods, including flow matching, which uses an optimal transport objective, and reflow, which compares to a standard two-stage distillation approach. We generate synthetic examples for both datasets, requiring multiple forward passes. Progressive distillation aligns with our method by distilling a series of student models from a pre-trained teacher. Consistency distillation involves generating pairs of data points and training a student model to ensure consistent predictions. We also introduce live reflow, which trains a model on both flow matching and reflow distilled targets simultaneously, although this method is computationally expensive. For evaluation, we assess models based on samples generated with different diffusion steps, using the Frechet inception distance (FID) metric. We report the FID 50K metric, calculated without compressing generated images, which are resized and clipped. Our results show that shortcut models excel in generating accurate outputs with few or one-step sampling, outperforming most prior methods without needing multiple training stages. Notably, while progressive distillation models lose the ability for many-step sampling, shortcut models retain this capability. Interestingly, our experiments reveal that shortcut models achieve slightly better FID scores than comparable flow matching models, suggesting that the self-consistency loss may provide implicit regularization, a topic we plan to explore further in future work. Additional visual examples are available in the supplementary section. Section Summary. In this section, we discuss our approach to distilling diffusion models into a one-step generative model, which is computationally cheaper and avoids the complexities of prior methods by learning end-to-end without separate pre-training. We compare our shortcut models to various existing methods, demonstrating their competitive performance in few and one-shot generation while maintaining the ability for many-step generation. Section. What is the behavior of shortcut models under varying inference budgets? In this section, we analyze how shortcut models behave when generating images with different step counts. While basic flow matching models use a simple tangent velocity to approximate the denoising process, shortcut models are designed to better integrate this process, leading to improved performance at lower step counts. Our findings, illustrated in a figure, show that while more steps generally enhance results, the drop in quality at low step counts is much more significant for basic flow matching models compared to shortcut models. We observe that shortcut models do not compromise on performance even at high step counts, maintaining the quality of baseline flow models. In contrast, artifacts from flow models often appear blurry or lead to mode collapse, while shortcut models typically avoid these issues, matching the quality of images generated with many steps. If a user wants to refine an image generated in one step, they can simply regenerate it from the same initial noise with more steps. Next, we explore how the performance of shortcut models improves as we scale up the model size. In deep learning, larger models often show enhanced capabilities, but this trend is less clear in bootstrap-based methods like those used for reinforcement learning. We investigate whether shortcut models can benefit from increased scale. Our results, shown in a figure, indicate that even with one-step generation, our transformer-based shortcut models produce more accurate results as their size increases. This suggests that shortcut models can scale effectively without significant collapse, achieving a one-step FID score of 10.6 and a 128-step FID score of 3.8 on ImageNet 256, as detailed in the appendix. We also examine whether shortcut models can create an interpolatable latent space. These models provide a clear mapping from noise to data, allowing us to interpolate between noise samples and observe the resulting generations. A figure displays examples of these interpolations, where we sample two noise points and create a smooth transition between them. The intermediate images appear semantically plausible, indicating that even without explicit regularization, the mapping is effective. While we do not investigate interpolation between existing images, it may be feasible to add noise to an existing image and interpolate those points. Finally, we assess whether shortcut models can be applied beyond image domains. Although our generative modeling objectives are domain agnostic, we traditionally focus on image generation. We test the versatility of shortcut models by training them for robotic control tasks, building on previous methodologies. Our approach involves training a model to predict robot actions based on observations, aiming to reduce the inference process to one step. We maintain the same network structure and hyperparameters as the original work, with minor adjustments. Our results, highlighted in a figure, demonstrate that shortcut model policies can perform well in robotic control tasks while limiting inference to a single function call, unlike one-step diffusion policies, which fail dramatically.